So far we didn't speak about the projective line, and I have to do that now, and I want to introduce the projective line as a one-dimensional analog as of the two-dimensional projective plane. So if we considered the projective plane, we defined our point set as taking, well, three-dimensional vectors and identifying scalar multiples. This space is often called the KP2, which is the projective space over K of dimension 2. And now we want to talk about KP1, which is the projective space of dimension 1, which is simply taking a two-dimensional vector space now and again identify scalar multiples. So if you like to think in terms of standard embeddings, you have a standard embedding here as well. So you have an x coordinate and a y coordinate, and well, each point on the, say, real line is represented by its corresponding projective equivalent, which is taken the x coordinate and putting on a y level of 1. By that we also get one point at infinity, which has the coordinates 1, 0 up to scalar multiple, and we can properly speak of points in KP1 as equivalence classes of points. So in a certain sense, we can consider KP1 as being the field K, which corresponds to all points on the number line, plus one additional point at infinity. So let us do some calculations here. Let us first introduce one more important concept. You have projective transformations on those lines, which are simply multiplications by non-degenerate 2x2 matrices. So now with that, we can take 4 points and calculate the cross ratio of them. So say you have 4 points, A, B, C, and D, and well, we can define the cross ratio of them simply by a corresponding ratio of 2x2 matrices. And you may see that we get exactly the same as we got in the two-dimensional case where we considered points on a line, because if you consider those points in standard embedding, and you can freely go to standard embedding because this here is a projective invariant, so you can assume that all your points are at finite position and are, by rescaling, in standard position. If you calculate this determinant here, it's nothing else as a difference between the 2 point coordinates, which is nothing else as the oriented length between these points. So this term here is really the same as we got in the embedded two-dimensional plane. I want to go to one special situation here and consider the 3 special points that I've given names here. This point 0, the point 1, and the point infinity, and they should sit at very certain coordinates: 0, 1 in the standard embedding, 1, 1 in the standard embedding, and 1, 0 in the standard embedding. And I want to calculate the cross ratio of some other point sitting at x point 1, and let's see what we get here. So if we calculate the cross ratio, we have to divide those two products of determinants, and if you look at those products, you see that everything cancels down very nicely, and what we are left with is a simple number x. So if we take those 3 special points here, 0, 1 and infinity, this point x here really reconstructs the value of this point on the number line here. So we really can consider this as a projective scale on that line. And if we use that and we plug in our other points at this position here, so if we plug in the point 0, we will get the number 0, and we plug in the point 1, we will get the number 1, and you can easily check if we plug in point infinity, we will get an infinite value. So this cross ratio together with those 3 points serves as a kind of translation tool that gets us from the projective world to the world of just real measurements. And since everything is invariant under projective transformations, we can use that to even define projective scales under perspective distortions. And here is a kind of, I would say, impressive example. So here I have the following situation. I've taken a picture of railroad tracks, and if you look at those screws that you have here, they are pretty nicely in equal distance, and by taking these two lines you can calculate the position of some kind a point at infinity here, and if you place 2 points 1 and 0 and 1 here, and a point x here and a point infinity here, you can calculate this cross ratio, and this is actually done in this example. And so you see, with respect to this point 0, 1 and infinity, this position of point x here gets a value of 2, which means it is really 2 units apart in our coordinate system. And this works nicely even if we move the points around. So here I take my point and move it now 3 units apart, and you see this is nicely reflected by the cross ratio. Here you have the situation where you are 4 units apart, and you really see here you have 1 unit, and you have here 1, 2, 3, 4 units apart to get this position of this screw. And with this I can be pretty sure that if I move my x to a situation where I get a cross ratio of 30 here, that these are exactly 30 screws from here to here. And I even can change my scale here by saying, well, my unit scale should now be 3 screw distances, and then you see you need 10 times this distance to get here. With that, I hope I gave you some impression of how useful cross ratios, in particular in connection with projective scales, are. And in our next slot, we will see how these two tools are really useful to even define a kind of multiplication and addition in purely geometric terms.